Hey y'all, today we are talking about converting between exponentials and logarithms. So before we get into it, I would like to do a quick refresher on our exponent laws. So for real numbers, b such that b is greater than 0 and n, we have the following. So first of all, b, any number, any positive number raised to the 0 is just 1. That's our first law. Second rule, b to the 1 is just b on its own. Hopefully this is something we remember. I think we've had to use this fact a couple of times already. It's just nice to have it written down. And last but not least, this one may be a little bit less familiar, b to the negative n. That means that we are raising b to the power of n, but since it's negated, we need to take the reciprocal. So that means we're looking at 1 over b to the n. That's what happens when we have a negative exponent. Let's talk about graphs of exponential functions. Just a quick introduction to these. We will do a lesson on finding the equation of an exponential function from a graph. But for now, all we really need to know is that if we have an exponential function, let's say we have f of x equals b to the x, where again, b is greater than 0, that's really important, then we have two options. If b is greater than 1, our graph is going to look like this. We have this sort of J shape. And if I have b between 0 and 1, my graph is going to have this shape.
On the left, we have this graph that's getting bigger as we move along the graph to the right. That's because every time we multiply by b, right, with the exponential function, right, as x is 1, we have 1b, as x is 2, we have b squared. Since b is bigger than 1, then the value of the graph is getting bigger. On the right, since b is less than 1, as x gets larger, we are multiplying again and again and again, and it's making the value of the graph smaller each time.
First of all, what's the domain here of these graphs? Well, we can either look at the graphs or we can look at the function, right? Let's look at the function. Are there any denominators or even roots? No, so we don't have anything to worry about. So our domain is all real numbers, which we can see from the graphs pretty clearly. Both of these graphs have a horizontal asymptote. I'm not going to write it all the way out, but horizontal asymptote at y equals 0, right? Along the x-axis, they're getting really, really close but not touching, which means what can we say about our end behavior? Just doing a quick review here of a bunch of different things. As x approaches, what can we say about the graph as we approach negative infinity and positive infinity for each of these guys? Well, for this one, as we approach negative infinity, right, that's what's going on as we move off the graph to the left, right? This is where the x's are getting negative. We are getting really, really close to 0. So y is approaching 0. As x approaches infinity, right, as we move off the graph to the right, our y values are also approaching infinity. Here, as we move off the graph to the left, right, as x approaches negative infinity, the y values are approaching infinity. And as we move off the graph to the right, as x approaches infinity, the y values are getting closer and closer to 0. So now that we've looked at that and gotten sort of a quick debrief on exponential functions, let's talk about logarithms. So definition, a logarithm, log base b of x, which, let's write it down in your notes. The way we say that is log base b of x is the inverse of b to the x. So, for example, if I have f of x equals 6 to the x, that means by our definition that we have f inverse of x that's equal to, well, we said b was 6, so then here b will also be 6. So we have log base 6 of x. So what does this mean? Let's look at a very particular example. So if I plug in to this function, let's say x equals 2. So then I would have 6 squared, right? X is 2. What is this equal to? Well, this is just 36. So what does that mean over here for our inverse? Well, let's think about what it means to be an inverse, right? The main idea with an inverse is that we're swapping our input and output. So what is our input here and what is our output? 2 is our input, right? That was what we plugged in for x. That's our input variable. And what we got from the function was 36. So this is our output. So now that means that over here, our input, x, should be our old output, so 36. So we have log base 6 of 36, right? This is our new input, is going to give us our output, right? Our output is our old input, right? Because we're swapping input and output, so it's 2. So from this, we can kind of come up with a formula, sort of, where we have b to the x equals some output a. And when we swap forms, right, that's what we're here to do. We're converting between exponential and logarithmic form. When we swap forms, this is our old input and our old output. So our new input and output, our new input will be a, and our new output will be x. This is sort of the formula that we're using here. So, right, in the same way that we swapped these guys, we're going to swap them in general in this way. So let's do another example really quickly. Let's say we're starting with log base 2 of 16 equals 4. We want to swap this to exponential form, right? It's in log form, so we want to swap it to exponential form. We have our input here, which is 16, and our output is 4. So when I swap, again, I need to remember to just swap the input and output. The last thing I need to remember is that I have a base of 2, right? The base of our logarithm is going to become the base of our exponential. So we have a base of 2, so that's the big one. Our input is going to be 4, because we're swapping, and then our output is going to be 16. And if I look at it, right, I got 2 to the 4th equals 16. Is that true? Totally. Of course, it should always be true, right? So this is our new input and our new output. Okay, let's give this a shot in the lab manual. So this is part 1 of the section converting between exponential form and logarithmic form. So I'm looking at the first one. I've got a log of base 3. That means for my exponential, I'm going to have a base of 3. Now I need to swap my input and output. My input, what's going into the function, is 81. So that is going to be my new output. So I'm going to go ahead and put it over here. And then on this side, we've got 4. That was my old output. Now that's going to be my input that's going into the exponential function. So I have 3 to the 4th equals 81. Let's try this one over here. First of all, I'm in exponential form, so that means I'm going to be converting to logarithmic form. So we have a logarithm. We have a base of 5, so my logarithm is also going to have a base of 5. Now, I need my input. Remember, we're swapping, so my new input, my input for the log is going to be my output for the exponential. My output was 125. So that's what I have on the inside. And it's going to be equal to what was my input before. My input was the exponent, right? 3. And so that's log form. Let's do number 6. We are in exponential form, so we want to convert to log form. What's our base here? Well, the base of the exponential function is just 4. Then our output becomes our input, so that's 1 over 16. And then our input is -2, so that becomes our output. We end up with log base 4 of 1/16 equals -2. Why don't y'all give number 8 a shot really quickly? Pause the video and I'll talk about it in just a second. Okay, hopefully this is what you got. We had an input of 1/2 and an output of 7. So for this one we had an input of 7 and an output of 1/2 with a base of 49. And of course it's in log form because we were in exponential form. Okay, let's go back to the notes really quickly. So we have a couple of types of really important logarithms. The first one is called the natural log. We call it the natural log ln of x. This is L for natural log, is short for log base e of x. What is e? Well, e is a special number that shows up quite a lot in math. That's equal to about 2.718. It has a lot of really interesting properties. It's kind of similar to pi, but they chose e to represent it. Another special log is the common log. The common log is just log of x, right? Log with no base. and it is short for log base 10 of x. So if we ever are missing a base, we know that it's 10. We're talking about log base 10 there. That is also a very important logarithm. If you see logs out in the real world, you're most likely to see the common log, but natural log will show up every so often as well. So let's look at a couple of examples of this. If you were to see something like ln of 20.086 is approximately equal to 3. How can we swap this? And we wanted to swap it into exponential form. How would we do that? Well, we could rewrite it if that helps. This is just log base e of 20.086 is approximately equal to 3. And when we swap the forms, we can now just do it business as usual, right? We have a base of e, so our exponential function is going to have a base of e. Our input was 20.068 and our output was 3, so that means our input will be 3. And this is approximately equal, so we do the squiggle. Our output is 20.086. Awesome. Similarly, if we have, for example, log of 100 equals 2, how can we swap this? Well, we don't have a base, but when we don't have a base, we know that it's the common log, so our base is 10. So let's go ahead and rewrite that. We have a logarithm, which means we're going to have a exponential. We're switching to exponential form with a base of 10. Our old output was 2, so that's our new input. And our old input was 100, so that's our old output. Is 10 squared 100? Yes, it is. So we are good to go. So let's do one example from here. So let's say we have log of 1 million equals 6. So we want to convert this into, well, it's a log, so we want to convert it to exponential. We don't have a base, so what do we know that our base is? 10. The base of our exponential is 10 because the base of our logarithm is secretly and silently 10, right? Equals 6. So our output from before, what this was equal to, is 6. So that's my new input. And our old input, 1 million, is our new output. So we have 1, 2, 3, 4, 5, 6 zeros behind there. And that's what we get. Why don't you guys take a second to try these three, numbers 2, 3, and 7. Pause the video, and then as you continue, I will talk briefly about them. Okay, so this is what we got. This one was very similar to the problem we did just now in our notes, right? We just swapped our input and output. We have ln, so our base is e. Similarly here, we had no base, so we know that it's a base of 10. So we had 10 cubed, right? 3 is equal to 1,000. Last but not least, we converted to log here. We knew that we have a log base 10 because that was the base of our exponential. Our input was 5, so that became our new output. And our output was 100,000. Oh, I didn't put enough zeros here. We're here. So we had this. We could have also written it this way, but I would totally accept this on a test or something else. So these are both correct answers. Sometimes we may not have all numbers when we are looking at log or exponential form. Sometimes we might have a variable in there. But when that's the case, we just follow the rules like normal. So let's say we were looking at x equals log base 7 of 7. We're in log form, so we want to get it to exponential form. We have a base of 7, so the base of our exponential is 7 as well. The input for our function here, there should be parentheses around the 7. There should be parentheses around all of these. The input for this function is 7, and the output here is x, right? This function is equal to x. So our output becomes our input, and our input becomes our output. So 7 to the what equals just 7. Well, if we recall our rules from the beginning, do our rules tell us anything about 7 to something just being equal to 7? Yeah, something to the 1 is equal to just itself. So then if 7 to the x is equal to 7, then x must be equal to 1. That's the answer here. Similarly, let's say we're looking at log base 3 of x equals 4. Again, we're in log form, so we want to convert to exponential. We're going to have a base of 3. My input is x. My output is 4. So my new input is going to be 4, and my output will be x. So x is just equal to 3 to the 4th. 3 to the 4th is just 81. Okay, looking at number 6, here we have 10 raised to the x equals 1,270. So we're in exponential form, we want to be in log form. So we have log base 10 of, well, our old input was x, our old output was 1,270. So our new input is 1,270 and our new output is x. If we know that x is equal to this is not something that we can calculate easily kind of in our heads. This is something we'll have to put into our calculator. How do I do that? There's an explanation of how to do that on a TI-36X Pro on the Desmos assignment. You can also find it on Google for sure. Clearly this is not a TI-36X Pro. I don't have one of those. This is a TI-84, which is actually not allowed on the tests for this class, but unfortunately it's all I've got at home right now, so too much. But I do want to show an important formula that we might want to keep in mind depending on what kind of calculator you have and whether it will do logarithms with different bases. If I want to calculate log base 10 of 1,270, I need to do log of 1,270 divided by log of 10. That will give me 3.104. So that means here x is 3.104. I want to write that down in our notes really quickly, that that's a formula we might need to use. So on older calculators, in order to find log base b of a, you may need to do log of a divided by log of b. So for example, if I was looking for log base 3 of 7, I could calculate that by finding log of 7 divided by log of 3. That would give me 1.771. one more thing while we're kind of talking about notation and calculator stuff and all of that. This is what we would call an exact answer. This is what, for the most part, WebAssign is going to want you to give. Whenever you have those big text boxes, it will want something that looks like this. This is the answer in decimal form, rounded to 3 decimal places. The reason this is not an exact answer is that we've had to round this number in order to even write it on the page, right? This number continues infinitely, right? It's an irrational number. So in order for us to even write it down, we have to round it. We have to chop off a bunch of information, right? So the only way we can write this answer exactly is by writing log base 3 of 7. You're ever asked for an exact answer, you want to leave it like this. Okay, so coming back here, right, log base 10 of 1,270 is an exact answer. And x equals 3.104, this should be approximately. This is a decimal answer. This is fine for now. Okay, let's look at number 3. Let's say we've got x equals log base 3 of 3 to the 15. So we've got log form. That means we want to convert to exponential form. We have a base of 3. Our old output, what it was equal to, was x, so that's our new input. And our old input will become our new output. So I have 3 to the x equals 3 to the 15. This is something called like bases. If we have like bases in this situation, 3 to the something equals 3 to the 15 means that this something has to be 15. So x is 15 here. All right, looking at number 7, we've got log of 100 equals x. Well, let's say we didn't have a calculator here. We are in log form, so let's convert to exponential. If we have no base, it means we have a base of 10. So we have log base 10 of 100 equals x. Our base is 10, so our base of our exponential will be 10. Our old input was 100, our old output was x, so our new input will be x, and our old output will be 100. X to 10 to the what equals 100? 2, right? 10 squared equals 100, so that's our answer. Last but not least, let's look at this one. Let's say we had e to the 2x equals 57. This is in exponential form, so we want to put it in log form. Our base is going to be the base of the exponential, which was e. Our old input was 2x, our old output was 57, so our new input is 57, and our new output is 2x. If I wanted to, I could change this to say ln of 57 equals 2x. That's totally fine. Now, I do need to solve for x here. So solving for x means I've got to get rid of this 2. It's multiplied by x, so I can undo by dividing by 2. So I end up with x equals ln of 57 divided by 2. Again, this is an exact answer. If it asked us for the decimal form, we would need to put it into our calculator. ln is usually a button on any scientific calculator, so we can just do ln of 57 divided by 2, and we get 2.022. I always recommend solving at least to 3 decimal places. Again, this is the exact answer, and this is decimal. Okay, let's look at our notes. All right, let's say we have 2 equals log base 4 of x plus 3. We're in log form. That means we want exponential form. Our exponential is going to have a base of 4 because that's the base of our logarithm. So we're switching forms. We have a base of 4. Our old input was x plus 3. Our old output was 2, so our new input will be 2, and our new output will be x plus 3. 4 squared is just 16, so I have 16 equals x plus 3, which means that I end up with x equals, I can subtract 3 from both sides, I get 13. Let's say we were asked to find the inverse of f of x equals log base 4 of x plus 3. We just kind of solved this when it's equal to a certain value, right? So we found the x value that would give us the y value of 2 here. So let's find the inverse. So what was our process of finding inverses? Well, we swapped f of x for y. So we have y equals log base 4 of x plus 3. We swap input and output, right? So x equals log base 4 of y plus 3. Now we want to solve for y. That's our next step. In order to solve for y, we need to get it outside of the logarithm. So normally our best bet there is to swap to exponential form. We swap to exponential form, we're going to have a base of 4. Our input is y plus 3, so that will be our new output. And our output is x, so that will be our new input. So we have 4 to the x equals y plus 3. Then all we have to do is subtract 3 to get y on its own, so we end up with y equals 4x minus 3. Last but not least, we rewrite it in function notation, so we have f inverse of x equals 4 to the x minus 3. And just as kind of a note, what we were doing here was finding, right, the x value that was going to give us an output value of 2, right? And remember, our inverse should tell us, if we plug in an output value, what the input value was. So if I plug in 2 here into the inverse, right, we're plugging in the output of 2, it should give me the x value that gave us that 2 from the original function. So if I plug in 2 here, 4 squared minus 3, I end up with 16 minus 3, which is 13. So this is good to go. It's all connected. Let's say I asked y'all to find the inverse of g of x equals log base 3 of 7 minus x. We rewrite the function with y. We swap x and y. We solve for y, which means getting it out of the inside of the logarithm, so we have to swap forms. We swap to exponential. Our exponential form has a base of 3 and input of x and an output of 7 minus y. We can add y to both sides. And then in order to get y by itself, we subtract 3 to the x. So our function inverse is g inverse of x equals 7 minus 3 to the x. That is the answer. Oops. Let's do one converting from exponential. Let's say we have this. We want to rewrite with y. So y equals 2 to the x minus 3. We swap x and y, so we have x equals 2 to the y minus 3. Now that we have it in the exponential, we want to swap forms. An exponential with a base of 2 is going to give us a logarithm with a base of 2. Our old input was y equals 3. Our old output was x. Our new input will be x. And our new output will be y minus 3. To get y by itself, we just add 3 to both sides. We end up with log base 2 of x plus 3. This means that h inverse of x is log base 2 of x plus 3. Okay, that's all I have for y'all today. Very exciting that we've introduced logs into our repertoire, and we'll continue to see more of them. Okay, thanks y'all.